Okay, now we change the value of M, K, and FV to different values. Let's say we change to M equal to 2. So yeah, M's 2 kilos. Yeah, I don't want to put the unit there. It's okay. FV is maybe remains 2, and then K equal to 1. All right. So our new transfer function will be 1 over 2s squared plus 2s plus 1. Then we will simplify this 1 over 2 over s squared plus 1 plus 0.5. Something like that, right? Okay, now we need to find this. Okay. We need to find roots. So the first root, so we are getting a complex root, which is 0.5 plus j 0.5, and then s2 minus 0.5 minus j 0.5. Okay, so now you see that the answer now change. Okay, the roots change, right? So if we were to plot that on the s-plane, right? So the first one, okay, that should be a complex conjugate here. So that's minus 0.5, right? That will be maybe 0.5 j, and it's minus j 0.5. So as you see here, the roots of the systems move to the complex plane, right? So it is no longer along this line, which is for underdamped systems. We have that. So from here we can say that the system is the first one. The system is stable, right? Because on the roots are on the left hand plane. Number 2, the response is underdamped, right? Underdamped, right? So we can see that based on the underdamped systems, we can sketch the response to be something like, if we push that, this is our YT, this is our YO, right? So when you provide the inputs to the system, which is minus FT, right, impulse input, and then we will start seeing that the system will will bounce, right? Because this is underdamped systems. It will oscillate depending on the damping ratio that we'll discuss later. But let's understand the concept first. So once we have this, we need to find parameters, right? We need to find the parameters you see in the slide on the right. There's a parameters in the second order systems. We have the first one is the rise time, TR, overshoots, which is the magnitude, the highest magnitudes over the steady state lines, and then the TS is the system time, the same parameter for first order systems, and we have damping ratio. We have one more peak time here, the time where the response reach at peak, right? So peak time, settling time. So there are 5 actually. So there are 5 parameters here. 5 parameters, right? We can determine from the second order systems. So whereas in the first order system we have only 3. Okay. So you see, as we change the value of M, K, and FV, damping, the behavior of the bouncer will change, right? And then the parameter will change too, right? So that is very very interesting to to study about the second order systems. Okay, now if let's say we were to change, based on this, if we want to change the the value of m to different value, higher values, so that we can further understand. Let's say we stick the value, maybe the same thing. We can increase. Let's say we increase to 1000. I know this doesn't make sense, but just for the sake of analysis of the systems, we maintain this. Okay, this is 1. Okay, so let's see this. Okay, our transfer functions will be 1 over 1000 s squared plus plus 2s plus 1, right? So we'll end up getting 1 over 1000, and then s squared plus 2 over 1000, s plus 1 over 1000. Okay, so as we can see here, if we increase the mass, okay, if we increase the mass of the system, right here, we increase the mass, and we assume that the baby is 100 kg, right? So when we push it down, right, with that spring, constant, and the frictions there, what happened to the systems, right? So the system will bounce. So this system will reach this is the root of that systems. We got this you can verify this. I just okay, plus, maybe this is minus J0.02. okay, you see that when you plot this on the S plane, right, we are getting unstable systems, J0.03 minus J0.03, right? So it has very low damping compared to the mass. So because we'll see that the system will becomes, okay, the first one is a stable system because it's on the left hand side, but the system is nearly overdamped, slightly, it's just above the real axis. That means it is close to the overdamped system, but it's still underdamped systems, right? So when we give a push, the system will somehow maybe bounce a bit like that, then stabilize. So it doesn't help. It could be this because of this is the final state of the systems. That means the final state of the system maybe is supposed to be at YO, maybe, somewhere else, because of the mass is very heavy, right? So this is steady state. Okay, now we understand that in second order systems there are 5 parameters. The response will varies from overdamped, can be overdamped, can be underdamped, or can be undamped. Okay, like I said, if we could bring this the roots towards the imaginary axis, and then our system becomes undamped, then it's a best system, right? For the bouncer, undamped system is the best, because when you give a push, it will bounce forever. But this won't happen in the real life. Okay, so we will have some frictions here and there, and then damping, so that cause the system to stop, right, to decay and stop, right? Okay, we stop here. So hope you understand. We continue to the next lecture.